recall what a little bit of what we did on Tuesday. So we defined the total variation distance, no? So given mu and nu, probability measures on some space omega that we are going to assume finite or countable, then the total variation distance between mu and nu this is equal to so it's 1/2 the sum over x in omega of this difference. Okay? It was also equal to the supremum over all the functions between 0 and 1 of the difference between the integrals of the function f with respect to the measures mu and nu. Okay, so I'm just now writing this the integral as a sum because it's actually just a sum in this discrete case, and this is also equal to the infimum over all couplings of mu and nu of the probability of the diagonal. Okay, so and the probability of the diagonal is just the sum over x in omega of big pi xx. Okay, so these are the three definitions of total variation that we have, and the fact that this distance is equal to these two here is a theorem. It's called it's a particular case of the so-called Kantorovich-Rubinstein duality theorem. Okay, so this thing here is what is called in the literature, in the discrete case, the Kantorovich duality. Okay, so this was generalized for by Rubinstein to more general.
Here maybe should be of the measure outside the diagonal?
Outside the diagonal, yes. Sorry about that. So it's 1 minus this number here. Okay? So now what we're going to do is that we're going to do some examples. So we are going to start with the simplest of all, and then we'll try to do things a little bit more complicated. So let's assume that, so let's take mu, the Bernoulli of parameter p, and nu, the Bernoulli of parameter q. Okay? Then the total variation distance between these two measures. So Bernoulli of parameter p is just the probability measure that gives probability p to 1 and probability 1 minus p to 0, or to minus 1. Actually, in this case here, it doesn't really matter because for the point of view of total variation, the labeling of the set omega doesn't really matter. Okay, so this is 1/2. There are two cases. Okay, so if x is equal to 1, we have to compare p with q. And if f is equal to 0, we have to compare y minus p with y minus q. And you can see that this is equal to just p minus the modulus of p minus q. Okay? So this is a very simple way to compute the total variation distance. A very simple exercise that I'm going to, a very simple proposition that I'm going to leave as an exercise is that the total variation is also equal to the sum of the difference of the positive part of the difference. Okay? Without the 1/2. So if this one here is mu, this one here is nu, the total variation distance is 1/2 of this area here. Okay? And what happens is these two areas are equal, no? Because this, the sum of the areas of these two regions here is 1. The sum of the areas of these two regions is also equal to 1. So it means that these two areas have actually the same value. Therefore, the total variation distance, which is 1/2 of the sum of the areas, is actually equal to each one of them. And this area on the left is this number here. Is the sum of the positive part. Okay? With that in mind, I'm going to do another example. So let's take now, instead of Bernoullis, binomials. Okay, with the same n but different p's and q's. Okay, so these are just sums of Bernoullis, right? We already know something, right? The total variation distance is a distance. Therefore, we are tempted to say that the total variation distance between mu and nu is less or equal than the sum, because we have random variables. We have that the binomial is a sum of Bernoullis. This is wrong in general, okay, because what happens is that the law of a sum of random variables is not the sum of the laws of the random variables. So this is not So this is something important that you have to have in mind, okay? When you take a sum of random variables, the total variation distance of the sum, you have two sums, no? So the total variation distance between the sum of two sets of random variables is not immediately related to the sum of the total variation distances. Okay? Anyway, this is binomial, this is binomial. Okay, so let's go and make another picture. So the support of the binomial random variable is the interval 0, n, right? The discrete interval 0, n. So we have n here. Let's say that the p is bigger than q. Okay? So how are the graphs of this random variable? So this is new. And this is mu. Well, so we just use the formula, no? So the total variation distance between mu and nu is equal to 1/2 the sum over and now x goes from 0 to n of the difference between, so it's n over x, p to the x, 1 minus p to the n minus x, minus, so I have the factor n over x again, so I can factor this 1, so you see here that so this is something you can check. Here it looks like this is the positive region, no? I mean, it looks like. It's not clear whether it's true or not that the difference, I mean, when you take the difference, there is one side that is positive, then there is a point here when you change sign, and you never change signs again. Okay? It's actually true. It can be seen from here, no? From this explicit expression. Because, so you can rewrite this in terms of p over q and 1 minus p over 1 minus q, and using the fact that the function p divided by 1 minus p is increasing. Okay? But the point here that I wanted to make that it's more or less clear that there is no closed expression for this. I mean, even if we are able not to say to figure out that this expression is positive up to some point x here that depends on p and q, this is still not, doesn't tell you much about the difference between these two instances. Okay, so this means that we really need actually ways to estimate these things. It's so a question here, no? How do we get let's say meaningful bounds both upper and lower for this total variation distance. From this picture, how do you expect? What can we expect about the total variation distance between these two measures? What is the order, more or less? Just looking at this picture. So the idea is that they look far, one from the other. What does it mean far in terms of total variation distance? One can check that the diameter of this space here is 2. No, is 1. So the distance can be at most 1. Okay? So the first thing that one can say is, so if P and Q are not close, then this should be, let's say this, no? This is equal to big O of 1. Okay? Important warning, no? The big O, little o notation is very dangerous in mathematics. Okay? You should not use the big O, little o notation in mathematics unless you know very well what you're doing. Okay? But if you are writing a vague statement which is not really a rigorous thing, so it's something that tries to give you some intuition about what we're doing, big O and little o notation is very good. No, because it's so this means that the distance should be more or less a constant, no? It should be maybe it's close to 1/2, something, no? Huh? Yeah. So we should try to see what happens when P and Q get close one to the other. So what do we expect when P and Q are close?
Yeah, when you mean closed, are we thinking of P and Q as functions of n, or are we thinking of them as fixed?
Both.
So I guess if they're different than fixed, then it's the same thing, right?
É interessante pensar na variância, então.
So yeah, so if P and Q are fixed, and n goes to infinity, what do we know about the binomials? We know that the binomial is concentrated around a region of size square root of n. So this peak that I drew here gets smaller and smaller, and it's of order square root of n. So, and then, and it's centered at this number, at n times p, n times q. So, if, let's say, p minus q is much bigger than 1 over square root of n, then mu minus nu in total variation should be equal to 1 minus little o of 1. Okay? They should be very far away, because the mass is concentrated around these two numbers here, and the distance is too big. Okay? So it means that this area here is almost equal to 1, because this one is almost 0 here, and the area of this one is all concentrated here. So if p minus q is of exactly order square root of n, so what do we expect? So if this constant a is very, very big, this thing that we were saying about the variance, which is basically where this square root of n comes from, right? What we call the standard deviation, will tell you that they are very big, so this number here is small, but not very small. Okay, so this line here, if I take a very, very big, is a number which is very small but fixed. Not very small but fixed, that does not depend on n. Therefore, this difference will be something like 1 minus a small number that depends on a. So there should be a function of a here. And there should be also a function of p, right? Because the position of p matters, no? It shouldn't be. It's not the same if p is near the middle, or if p is near the border of this interval here. Okay. So this is all just a hand waving around the fact that the binomial looks like a Gaussian when you send them to infinity. You know, this is the Laplace de Moivre theorem tells us that the density of the binomial converges to the Gaussian function, right? And the region on which this convergence happens is a region of size square root of n around the mean. Okay, this is the Moivre-Laplace theorem. So all these things should be true. And then if p minus q is much smaller than 1 over square root of n, then this should be of order little o of 1. And here is meaningful to start to think about how depends this little o of 1 as a function of p and q. It is linear in p and q. It's proportional to the difference, to the square root of the difference, to the square of the difference. Proportional to what? We see that, for example, in the case of the Bernoullis, the total variation distance when p is close to u is proportional to the difference. Yeah.
I want to understand the intuition in the last one because it feels very weird to me. Because say you take p to be 1 over n and q to
of course,
be 2 over n.
You have to take p and q far from the endpoints.
Okay.
Okay. So this is something. It's an important point. When I say this, I implicitly assuming that they are not close to the boundary.
Because otherwise it's a Poisson.
Yeah, exactly.
Should I expect the total variation distance to converge to the total variation distance of the respective Poisson?
Yes. So this is a very important observation. The total variation distance is a distance. Okay. So a property of distances is that they are continuous, just by definition of what is continuity. So if you have convergence of some probability measures to something, then the total variation distance is also convergent. And so what I just said actually is not mathematically rigorous. What I'm saying is that the topology of total variation, the topology induced by the total variation distance on the set of probability measures is stronger than the topology of convergence in distribution. No, it's not stronger. It's a metric. Yeah. So it's a metric for the convergence on distribution.
For the convergence in distribution or for the convergence in L1?
Yeah, in distribution, but the caveat is that the space is not closed, so You cannot converge to the, if you don't converge to the border of the space, you're okay.
But is this not the same as L1? At least
It's the same as L1.
and in this other case, I guess they're the same.
Yeah.
Okay, sure.
So okay, so these are just things that we can expect. But the question now is, okay, yeah, but can we prove this? Can we show that this is actually true? How do we do that? Okay. So, and the answer, some of the answers to these questions are contained in the Kantorovich duality. Right? Because the Kantorovich duality tells us how to get upper bounds and lower bounds the other way around. Lower bounds and upper bounds on the total variation distance using functions and couplings.
O maiúsculo e depois o minúsculo? Ou todos?
É minúsculo. O primeiro é maiúsculo e todos os outros são minúsculos.
Então a variável aleatória seria isso em outra observação?
Hã?
O maiúsculo é uma variável aleatória?
Não, que isso aqui é um número. Isso também é um número.
Por que o maiúsculo e o minúsculo?
Porque tem significados diferentes.
Ok.
Isso aqui se chama notação de Landau.
Eu não conhecia.
Tá bom. Mas você depois pode dar uma olhadinha. O nome disso é notação de Landau.
Landau.
E é muito usado em física. E em matemática também. Mas a gente tem que ter muito cuidado. So,
E aqui também a gente não falou nada sobre o N. O N tem que ser meio que grande, assim, relativamente.
isso. Exatamente. Então, exatamente, é isso que quer dizer essa notação O, que quando você pega um N muito grande, é isso aí que acontece.
Much smaller. What you're saying is that one side is a little low off the other, right?
Yeah. So let's try to see if we can say something meaningful about those things. So let's try to formalize the idea that we have about variances or standard deviations or whatever it was. Okay, so there is a theorem. So I'm not going to state the theorem. So this theorem, you can find it in the book of Levin WILMER, and you can find there a very clever proof that will give better estimates of what I'm going to do now. But it has a disadvantage that the proof is too clever. Okay, and we can do a proof which is worse, but it's like it's a little bit like let's try to formalize this vague intuition that we have. Okay, so the intuition that we had was this, no? So there was this. So let's go back to the picture. So we have that this was mu, no? And this here was new. Was the other way around? Well. Good that the distances are symmetric. So now, there are these points, no? So you see that this set here I'm going to call A. No. It looks like it has a big probability, a big measure with respect to mu and a small measure with respect to nu. So what we know is that the total variation distance between mu and nu is bigger or equal than choosing in this formula here the function f as the indicator of A is going to be less or equal than mu of A minus nu of A. Do we agree on that?
That's a weird application of the theorem, no? It should be equal, or no? Or am I missing something?
It should be equal if this set A is exactly the set on which this difference is positive. But it's a set on which I know is positive, but it's not the maximal necessarily. It's less, it's bigger or equal.
Okay.
Okay, because maybe, but this is actually true for any set A. If I take a bad set A, this difference is negative, so it's So now what we are going to do is that we are going to take x. No, I'm going to do that. I'm going to take A as the set x minus np is smaller or equal than b, than some constant b. Maybe A from A. Okay? This is going to be my set A. Okay? So it's not all this set here, it's just a piece of it. Okay? And then what we are going to do now is that we are going to estimate mu of A and nu of A. Okay? So mu of A complement, it's equal to, and now I'm going to do the following. I'm going to take x, a random variable with low binomial np. Okay. Then the measure mu of the say A complement is exactly the same thing. So it's mu of x minus np bigger than A. So this is equal to the probability of this random variable x minus its mean. Observe that this is the mean of the random variable x bigger than A. So now we can use Chebyshev inequality to say that this is smaller or equal than the expectation of x minus np to the square divided by A squared. Okay? And this expectation here is equal. The expectation above is just the expectation of a binomial, that is n p1 minus p divided by A squared. Okay? So that's 1/2 of the argument. So this is this means that mu of A is actually bigger or equal than 1 minus this number here, np 1 minus p divided by A squared. Okay? Now we are going to assume, I'm going to assume that P is smaller than Q. Okay, yes, that's why it was, I did the other way around. Okay, because, so this is NP, this is NQ, and this number here was A, somewhere in the middle. Okay, and so I'm going to assume that A, so I'm going to assume that NP is between A is between NP and NQ. Okay? Then, nu of A, it's equal to nu of X minus NP bigger than A. Under these conditions here, this is smaller or equal than the following set. So this one here, so we have NP here, we have A here, we have NQ. This set here is this one here. And this one here is this whole interval plus another interval to the other side. So it contains this interval here. Okay, so this set here is bigger than this set here. It contains this set here. Okay? Sim?
Um detalhe, ali tá muito parecido com NP1 menos P, mas ficou muito parecido com NPA menos, sabe? Só porque... Não, aqui, depois das... No outro lado. Depois da esperança, logo depois da esperança, o NP1 menos P, aquele parênteses 1 tá muito parecido com A.
Ah! Isso.
Ok, obrigado.
Então, agora aqui, so now what we're going to do here is Chebyshev again. Okay? So this is smaller or equal than the expectation. So now, I'm going to define another random variable y, which has binomial, but now of parameters n and q. And this number here is going to be less or equal than the expect. It's less or equal the probability of y minus nq bigger than nq minus a. Okay. And this is smaller or equal than the expectation of y minus nq to the square divided by nq minus a to the square, which is equal to n q 1 minus q divided by nq minus a to the square.
Sorry, I'm a bit confused in the first line of this last part. So this should be mu of a complement, or maybe you have the greater switch with the less than or equal?
Yes, so here is less or equal. Now that's good. Yeah. So this is this interval here. And this interval here is smaller than this interval here plus the one to the other side. Yeah. You see, here I could have won a factor 1/2. You see why? Because of symmetry. No, I'm taking this interval and the other interval. And so, with some symmetry argument, I could have won maybe a factor 1/2 or something like that. But let's not worry about that, because this is not really important in terms of factors. So we get this bound here. So the conclusion so what we conclude now is that the total variation distance. So let me write it like this, so we are clear what we are doing. No? So this is the binomial NP minus the binomial of parameters NQ. So this is a bigger or equal 1 minus MP 1 minus P divided by A squared minus NQ 1 minus Q divided by NQ minus A to the square. Okay? So there is some minimization problem now. What is the best value that we can take here of A? So, okay, so we are lazy. We can take derivatives and compute the exact minimum, no? But it shouldn't be very different from the average. So the average should work more or less okay. Okay, so this is for NQ smaller than A, NP smaller than A smaller than NQ. So let us take A equals to N P plus Q divided by 2. Just because this one is easy, no? To compute. So we get bigger or equal than 1 minus NP 1 minus P divided by N squared P plus Q divided by 4 minus NQ 1 minus Q divided by N squared P plus Q T cuadrado, sí, divided by 4. Well, magically then these two numbers are equal, no? No, they are not equal. Okay, yes, because actually here A is not this number here, no? I made a mistake. No. Minus NP. So here we have A minus NP. A minus NP. And here is A minus NP. Which is more reasonable because these two estimates should be symmetric, no? So So here this one is wrong, this one is wrong. So here is a minus mp to the square. And if we do that, when you take the difference here, you get n times p minus q. So we get n p 1 minus p divided by n squared p minus q to the square divided by 4 minus n q 1 minus q divided by n squared p minus q to the square divided by 4. So we get 1 minus 4 times p 1 minus p plus q 1 minus q divided by n p minus q to the square. And this one is exactly this claim here. Right? Because if p minus q is bigger than this number, then, so let's say that p minus q is equal to a very big constant a here divided by square root of n. Here it will give me a very big constant a squared divided by n, the n cancels, and what we get here is 1 minus some number divided by a very big constant. Okay? So it means that unless the difference is of order 1 over square root of n, this difference is very, the distance in total variation is very close to 1. Okay? So this bound here has a name, okay? And it's called Wilson method. Okay? So what we just did here, it's something called Wilson method. Okay? And it works with a lot of generality. Okay, so you are encouraged to look at the book of Levin Perez WILMER to take a look at this Wilson method, because it's very general. It doesn't require that the measures to be defined on an interval. Okay, because if you think about what we did, what you had to find is just a clever function x, a clever random variable x here, that has some distribution with respect to the measure mu, and some other distribution with respect to the measure nu. Okay, so we were later maybe I will give you some other example. So this is okay. Okay. Espera aí. É maior. Ah?
Porque o argumento é maior que A só, né? Mas ele está A menos NP.
Ah, sim. Então aqui eu tenho que definir assim, não? É isso, né?
É ou ali pode ser maior.
E. Sim. Então, so now the question is, how do we prove the other way? No, so it means if this difference is small, then they are close. Surprisingly, there is another method that is similar to this. It's basically the same computation, but it gives now an upper bound. Okay? So let me show it to you. Okay? So now let's try to find a bound in the other direction. So this is equal to 1/2 the sum over x of mu x minus nu x. And let me write this as the following: 1/2 of the sum over x of mu x divided by nu x minus 1 times nu of x. Okay? Now let's compute what is mu x divided by nu of x. So this is n choose x, px, 1 minus p to the power n minus x, divided by n choose x, q of x, 1 minus q, n minus x. Okay? So the factorials cancel, and we can write this in the following way. So we can write it as p divided by q to the power x times 1 minus p divided by 1 minus q to the power n minus x. Okay? And remember that we are assuming that p and q are close. Okay? So it is good to do some pre-processing here and rewrite this as 1 plus p minus q divided by q to the power x times 1 so here there should be a sign maybe. So let's check if this is correct. So I write it. So here there is a trick here you do when you are teaching, no? That I don't remember if this sign is plus or minus. So what you do is that you write a minus, because then you can correct it without erasing. Okay? Very important trick. Someday you will teach, and that's and let's see. It's 1 minus q minus p plus q. It gives you 1 minus p. Okay, so the sign is correct. Okay? So well, there p was smaller than q.
Okay.
So now, what can we do? So I'm going to rewrite this in here as the following. I'm going to write it as the exponential of x times the logarithm of 1 plus p minus q divided by q plus n minus x times the logarithm of 1 minus p minus q divided by y minus q. Is that correct? So if x is a random variable with loss binomial of parameter n and q, then this total variation distance can be written as 1/2 the expectation of the norm of this function here. Okay, this expression looks complicated, so let's try to understand it in steps. So the first thing is that if x has this law here, then the expectation of any function of x is equal to the sum of that function times the measure nu x, because nu x is the law of the binomial. Okay, so what I'm saying is that the expectation of any function of the random variable x is just the sum over x over little x of f of x times nu of x. Okay? So this is the formula of the expectation. And what I'm doing here is just observing that the total variation distance can be written as the expectation of some complicated function of x. Sim, mas aqui eu quero ter uma cota superior. E se usar a dualidade, eu vou ter uma cota inferior usando esse. So now we are going to assume the following. Q is fixed as a function of n, and p minus q is equal to some constant that I'm going to call a divided by square root of n. Okay? So if q is fixed and q is different from 0 and 1, then I can always take p equal to this, no? Such that the difference is equal to this for n large enough, no? Because actually if q is 0.01 and a is equal to, let's say, 1, then I have to take n bigger than 10 to make room for p to be at the right distance of q. No, but and now we want to see what happens with these numbers here. So you see that now I have the log of something of 1 plus something small. Since I have the log of 1 plus something small, I can write that as something small plus something even smaller. What I mean, okay, so one has to be very careful when one does this type of computation, is that the logarithm of 1 plus x, it's equal to x plus, well, actually it's minus x squared phi of x, where phi of x is smaller than something if x is smaller than something, no? So this is a Taylor formula, no? So let us discover what are the somethings. So Taylor formula says the following: the logarithm of 1 plus x, it's equal to, so we have to take the derivative, no? So the derivative of log 1 plus x is 1 over 1 plus x. We evaluate at x equals 0 is 1. So the first term in the Taylor formula is 1, x. The second one, so let me remember, if there I have to go to level 2 or to level 3. Level 3. It would be very nice if we go to level 3 there in the Taylor formula. So the derivative of this one here is minus 1 divided by 1 plus x squared, right? So the next term in the expansion of Taylor's formula is x squared divided by 2. Take the one extra derivative, you get 2, 1 plus x to the cube, right? So the next term is plus, so it's 1/6. It's x cubed to the 6th times the derivative at a point between 0 and x. So times 2 divided by 1 plus so this is Taylor's formula with Lagrange rest. Okay, so this is Taylor formula and this is Lagrange rest. Okay? And what is nice about the Taylor formula with Lagrange rest is that it is an identity. It's not an approximation. So here what we can do is that we can rewrite that expression there in the following way. Log of 1 plus x, it's equal to x minus x squared divided by 2 plus x cubed divided by 3 times the function phi of x, where phi of x in fact, phi of x is positive, is always positive. And the worst that can happen here is that if x is equal to, let's say, minus 1/2, then this is 1/2. If this is 1/2, this is 1/8. It goes to the other side, it's 8. So this is between 0 and 8 if x is bigger or equal than 1/2. Okay?
There's maybe a 6. Ah, no, sorry.
Because the 6 and the 2, I put it in here in the 3. Okay? Doesn't really matter, no? But I just to say that you can actually kind of estimate the constant in a very precise way. Okay? So this is something that people in general don't care about, but this is something I checked. So you know about you probably heard about confidence intervals in polls, no? Election polls. So there are these two candidates. They go to second round and they go one against the other, and you do an election poll, and they say, well, you're watching the news and they say candidate A is getting 56% of votes, candidate B 44% of the votes, with 2% plus or minus. So that means the confidence intervals is 2%. So what usually people do is that they say, okay, so I assume that these numbers are random, and I want to know, and I want to give an interval in such a way that I'm sure that what I did, the actual number that I'm sampling, is inside this interval with probability bigger than 95%. So this is what people do. Okay, so you say that the candidate A has 56% of the votes. Okay, plus minus 2%. What does it mean? Okay, it means the following. It means that the probability, no? So this number 56% is x1 plus xn divided by n. Okay, so you ask people, no, n people, who are you going to vote? Candidate A, candidate B, candidate A, candidate B. If they don't know, you don't count. In this particular way to do this poll. Okay. Then this number, this 56%, is this number here, and so you call this x bar. What does it mean? It means that the probability of xr belongs to the interval 0.54, 0.58. Okay. This is bigger or equal than 0.95. Okay. So this is what it means, plus minus 2%. Okay. And this is how election polls are designed. Okay. And then, if you do some computation, you assume that these numbers, the x1, xn, etc., have some law. Then the law/slash numbers, the central limit theorem, and more sophisticated estimates, if you want, there are the Chernoff bound, etc., blah 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 blah, tells you what is the n that you have to put here, such that this is true. Okay, and then you know. So what people do, and this is very sketchy. This is one of the main problems. Well, it's not one of the main problems. There are many other problems which are more serious right now, but this is one. This is a small problem, but this is still a problem which has a mathematical interpretation. So it's nice to talk about it. If you go to this is something I did. No, I enter into the. You know, there is a place on which you can read how the elections were done. What are the data? This number n in particular, you can go there, and there is a table in some website of the government where you can see, no? Well, if you want to do an election poll and you want a confidence interval like this with this rejection probability, then you have to take n equals to 2000. That's more or less the magical number. And then you see how they arrive to this number n 2000. And what they do is that, let's assume that each one of these random variables x1, xn is a Gaussian. So you're not shocked. Huh? Yeah, right? Because each one of these random numbers is either 0 or 1. And in the first line, what they do is that they assume that these numbers are Gaussian. Okay. So what people say is that it doesn't really matter because this is because of the law of large numbers, then this number here is close to Gaussian and then it's okay. This is correct if all these Bernoullis has the same parameter p, because the parameter p is very close to 1/2. What is the problem with that? This is not true, because when you are making a poll, a well-designed election poll, what they're going to do is that they're going to select some cities in Brazil at random with a distribution which is proportional to the density, to the population of the city. Once you do that, what happens is that if you go to a place like Santa Catarina, and then to a place like Pernambuco, which are states more or less of the same population, you probably know that the answers that you are going to get are very different. It's not the same parameter. So a well-designed election poll should take all these things into consideration. And not only, this is not the only problem. There are other problems which are very serious nowadays because people don't really answer when you ask. So there is a very big bias to people who actually answer. And people who actually really answer are not representative of the population. So in Chile, there was this company was very famous for making very good election predictions. So they managed. There was an election in 2000. So Chile has a population of 18 million. At that time, was a little bit less, but the election went to second round. And both candidates get above 48% of the votes. So statistically speaking, it was extremely difficult to actually predict that the election was going to second round, because both candidates were getting almost half of the votes, and no other candidate was getting a significant amount of votes. So these guys, they took a very big gamble because according to their numbers, they could predict that the election was going to second round. And why they were so confident about it? Because they had the following way to do this poll. They had an urn. So in Chile, you write your vote on a piece of paper and you put it inside an urn. So they have a real urn, and they go knocking door by door people, filling a form, some form about age, sex, place of birth, etc., average income or something like that. And the poll was done in the following way. So there were a lot of votes already cast inside the poll. So to make sure that, and they give a vote to the person, a piece of paper. The person actually cast the vote, fold it, and put it inside there. So in that way, they were actually making sure that the person was given an honest answer, and the rejection was very small because people were not afraid of actually saying the truth, and because there were lots of votes in the already, people were kind of confident that they were not going to identify what they were saying, and they get very, very small numbers here and here. And they did a lot of this. It was like 10,000. So that they could predict actually that and the margins were minimal, no? So, what is so this of course all these stories always has a lesson behind, no? The lesson behind is that statistics is a very, very, very powerful tool in science. But in order to be very powerful, has to be done properly. As anything, no? The problem with the statistics is that it's very easy, actually, to not do it properly. Because if you're not really you don't need to be super expert, okay? So because what I know about the statistics is very basic. I mean, I only have like 1 or 2 undergrad courses in statistics, but that's enough to be able to detect whether something is well done in terms of statistics. And it's a very powerful tool that can be used very poorly. As usual, no? I always like the example of the hammer, no? The hammer, you know what a hammer is, no? It's a very, very powerful tool. Try to put a nail without a hammer. It's basically impossible. Maybe you have a rock. Yeah. Now try to take out a nail without a hammer. That's absolutely impossible. No, it's an extremely powerful tool for exactly that purpose. Of course, you can do other things with a hammer. No, I'm not going to tell you. You can imagine. It can be used for many other things, which are not really the proper use of the hammer. No. So this is true with any tool. No. Tools are very powerful, but has to be used in the correct way, and it's important to learn to use all these tools in a correct way. Of course, okay, all this discourse is pointing in some direction, which is important for mathematicians nowadays, which is, you know, right? What I'm going to say now, which is a very important tool that we as mathematicians should tell the world how to use properly. So nobody really knows what the AI does, but the only ones that can explain why we don't know are the mathematicians. Okay, so now we have this number here. Okay, and what I was doing here is that I was trying to be very specific about this constant, okay? Because this is related to this problem here. Going back to this problem, if here you put instead an 8, a 20, or a 40, when you go to these computations there, here you get multiplicative, the multiplicative errors that you make in these constants here go to this number here. So it's actually it's good to try to estimate them good, to make good estimations on that, because this number here will appear in front of this factor here. And if you want to get this factor down, you have to double the samples here. And this is, if you are doing proper statistics, this is very costly, as I explained to you, no? Because as you can imagine, taking an urn and going door by door and bringing this urn all around Brazil. So it's important to actually put values to the constants, at least in some cases. So doing that, here, what we see is that. So let me write this, okay, as 1/2 the expectation of f of x minus 1. Okay? Where this function f is this function here. Just to not so then let's see what happened with the function f.
Essa é aquela coisa de Neyman, que eles usam muito inferência quando vai mostrar teste de hipótese, tem essa exponencial desses parâmetros, vem disso.
Na verdade, o que acontece é que se você, quando é muito comum em estatística você ter um monte de Bernoulli, porque as medições em geral são sempre 0,1. Só que as Bernoullis têm parâmetros que você não conhece. Aqui, se você quiser, você pode colocar parâmetros diferentes. Então, é um pouquinho diferente, mas é parecido com isso aqui. Para fazer isso, você usa outra distância aqui, que seja mais apropriada para o critério de fatoração. Porque cada distância, ela tem... ela é útil em diferentes situações. Essa aqui, em algum sentido, é a mais forte de todas. Sendo a mais forte de todas, às vezes não dá para estimar. Mas se você conseguir estimar essa aqui, como é a mais forte de todas as distâncias, aí qualquer outro critério vai passar. Vamos lá. So let's see what's happening with this function f. Okay? So it's the exponential. So we use that expansion there. So we get p minus q divided by q minus p squared divided by 2q squared plus p minus q cubed divided by 3 q to the cube times 5 of p minus q divided by q. This is one factor, and the other one is n minus x times minus p minus q divided by y minus q plus p minus q squared divided by 2 y minus q squared. And maybe here there was a minus. Let me see if there was a minus. No, there was not a minus. There's a plus. It's okay. So here is a minus 2. And now there is also a minus because it's a negative number. I'm assuming that p is bigger than q, okay? So this p minus q is negative. Or no? No, not necessarily. Here I'm not assuming anything. I don't need to assume anything. 3 times y minus q to the cube times 5 of p minus q divided by y minus q. And now let's remember that p minus q is a divided by square root of n. Okay, so I have factors of order s square root of n. So I have a divided by square root of n times x divided by q minus n minus x divided by 1 minus q. Minus a squared divided by 2n of x divided by q squared plus n minus x divided by y minus q squared. Okay, yes. And then there is a to the cube divided by 3 n to the 3 over 2 times x divided by q cube phi of p minus q divided by q plus n minus x divided by 1 minus q to the q times phi p minus q divided by 1 minus q. Okay, so this looks very ugly, but actually it's a very beautiful formula. Because, so let me do, okay, I can erase here. Because x divided by q minus n minus x divided by 1 minus q. So this is equal to x times y minus q minus n times q plus x times q divided by q 1 minus q. And this is equal to x minus nq divided by q 1 minus q. Okay, so I personally find this formula very nice because it's actually, this is a random variable, right? This is the mean, and this is the variance. Aside from a constant, no? But it doesn't matter because there are constants everywhere. And in fact, so not really, because you have to divide by the square root of the variance, but so you have here something which is nice, okay? So you have a divided by q, 1 minus q. So that's the first factor, times x minus nq divided by square root of n. Okay? So this factor is nice, because this is actually converging to a Gaussian random variable. In particular, this is of order 1. So when you take expectations on it's going to be like bounded by something nice. Then we have minus this number here. So that number here is a little bit more complicated, okay? So let's compute it here. X divided by q squared plus n minus x divided by y minus q squared. This is equal to x y minus q squared plus nq minus xq squared divided by q squared y minus q squared, which is equal to x y minus 2q plus nq divided by q squared y minus q squared. So this one is it's a funny number because you see that if q were equal to 1/2, this is 0. Okay? So if q were equal to 1/2, that number here, that random variable here will be actually not random because the x part cancels. But well, it is what it is. So we have this. We have a divided by 2 q squared 1 minus q squared times x y minus 2q plus nq divided by n. The important part is that this number here is bounded by 1. Is it bounded by 1? So this is bounded by n. This is bounded by nq, 1 minus q divided by n. So this is the biggest that it can be. So let's assume that q is smaller than 1. So the biggest is 1 minus q. So this number here is bounded by the maximum between q and 1 minus q. Well, this number here, this is I cannot do anything with this one. Okay, because there are these functions phi that are bad. But what I know is that I can write this as a cube divided by 3 square root of n times something that I'm going to call r. Okay? And r is bounded because this guy is bounded by n, this guy is bounded by n, and I'm taking one of the n's here inside this. Okay? So it means that this guy is small. Tem quadrado no A. Aqui. Obrigado. So here, I'm going to write this as a lemma, okay, because maybe my time is not okay, but maybe it's not that it's not that that interesting for you right now. But the lemma is that take z equal to a Gaussian random variable of parameters 0, 1. What we know, okay, so let me erase, so I can erase this one here. I can erase all this computation. That one no, because I'm going to use it in a minute. But what we know from the central limit theorem is that x divided by nq divided by square root of n. So you have to divide by the square root of n, q1 minus q. You have to divide by the square root of the variance. This converges to the random variable z, which has law 0, 1, normal 0, 1. This is what we know from the central limit theorem. Okay? Write it. Let me write it like this. So what we have is this limit here. Okay? So let me remind you that x minus nq divided by square root of nq1 minus q. This in here converges to z. We also have this identity. This identity, you have to use it here. Okay? So what is the idea? This factor here, according to the formula there, converges to z times square root of q1 minus q. The square root of q1 minus q cancel with this one here, and you get a divided by square root of q minus q. So you get the first factor here. If you take the limit in this expression, the second term, x divided by n by the lower large numbers converges to q. So here you get q, 1 minus 2q, plus q, which is the formula above. So it's 2 times q, 1 minus q. The q1 minus 2 cancel, and you get a squared divided by q1 minus q. There might be a 2 somewhere that I forgot. But, well, doesn't matter. And the third term, this one here converges uniformly to 0, because actually this is bounded by a constant. This is not random. Okay, it's random, but the bound is not random. It's just bounded by a number divided by square root of n. Okay? So, in principle, the lowest large numbers and the central limit theorem are not strong enough to give you the convergence of this expectation, but you can do it. Okay, so it's still true. Okay, if you are interested, we prove this in a paper that I can give you a reference later. So we have this convergence. Okay, so this is a Gaussian random variable. So what is interesting about this thing here is that this proves the other two facts that I mentioned at the beginning, right? So what we are doing here is that we are taking binomials and we are comparing them, and we want to see whether the total relation distance between them is small or not. And I told you, if the difference between p and q is bigger than 1 over square root of n, they are very far away. If the distance is exactly of order 1 over square root of n, then they start to get close. But if the distance between P and Q is smaller than square root of 1 over square root of n, then they are very close. And this is actually, this theorem is telling you exactly that. Right? Because if in this theorem you take A equals 0, here you get 1 minus 1, so it's 0. So the distance is 0. So if you take here an A which goes to 0, no? That means that P minus Q is of order smaller, it goes to 0 faster than 1 over square root of n. Then this number goes to 0 instead of going to this number, to a positive number. So the transition between being far and being close is exactly at 1 over square root of n. And we are able to describe it in a way which is, and this is very nice, it's universal. Okay, what does it mean universal? Means that the function that we get here does not really depend on the parameters. No, because you see that actually there is a hidden parameter, there is a unique hidden parameter here, which is this one. Right? Because if I here, if from the beginning I take P minus Q equals to A square root of Q, 1 minus Q, divided by square root of n, then in this formula there is no P and Q, there is only A. And this is something that somehow happens. And so when you have when you are comparing distances between probability distributions, if these probability distributions are somehow sums of small error terms, then the distance between them in total variation goes to something that you can describe in terms of Gaussians. So it's a kind of improved version of the central limit theorem. Okay, so this is so I have a few minutes. So as you can see from these computations, actually compute total variation distance is difficult, right? Because binomial is probably one of the easiest that you can do. So let me do another one. So I'm going to focus now on the upper bound. Okay. So let me do another example. I'm going to take mu with the Poisson of parameter, let's say A, and nu, I'm going to take it Poisson with parameter B, and I'm going to assume that A is smaller than B. Okay, so and I want to estimate the total variation distance between them. Okay, so the idea is to use coupling. Okay? So what I'm going to do is the following. I'm going to take x, a random variable with law Poisson of parameter A. And here when you do couplings, you have to be very clever. So what I'm going to do is I'm going to take y of Poisson of parameter B minus A, and I'm going to take y independent of x. Okay? Then, what happens is that x plus y, the law of x plus y is Poisson B. Right? Okay, so let us try to remember what is a coupling. A coupling is a probability distribution on the product space such that the first marginal is the measure mu and the second marginal is the measure nu. So if I look at this vector here, this is a random vector. Okay, so the law of this random vector is a probability distribution on the product space. So it's in this case, it's a probability distribution on the two-dimensional integer lattice. No, so n0 times n0. So it's the integer quadrant, if you want. Okay, so it's a law on the product space. The first marginal has the law of x, which is mu by definition. The second marginal has the law of nu by definition. Observe that this coupling, these two random variables are not independent, right? Because the random variables which are independent are x and y. But x and x plus y are not independent. In fact, x plus y is always bigger. So the total variation distance by the variational formula with the infimum is smaller or equal than the probability of x being different from x plus y, which is actually the same as saying that y is equal to 0. And what is the probability of y being equal to 0? The parameter of the Poisson. So it's e to the minus b minus a. Different from 0. Yes, sorry. And then this is equal to 1 minus the probability of y equals 0, which is equal to 1 minus e to the minus b minus a. Okay? So this is the bound that we have. The total variation distance between mu and nu is less or equal than 1 minus e to the minus the difference. Which, if you want to, no, this is a very useful bound that you can have, no? 1 minus e to the minus mu is always smaller or equal than u. So this is less or equal than b minus a. Okay? So when b minus a is small, this bound is good. Okay? So if b minus a is big, maybe you lose a little bit because but in general we're interested in the region in which they are close, no? So this bound is good enough for all our purposes. Okay, so well, this is just to show you how to estimate using coupling. Okay, very good. Well, I think I'm going to stop for today. So, yeah. So see you tomorrow, right?